NENOMATICA, where mathematics meets YouTube excellence. Example: we will follow a simple algorithm based on Vieta's formulas. Our quadratic is x squared minus left parenthesis k minus 50 right parenthesis times x plus 87 equals 0. Step 1. Identify product and sum of the roots. Product p equals 87. Its factor pairs are 1 times 87 and 3 times 29. The sum s equals k minus 50, so k equals s plus 50. Step 2. Make a small table. Use each factor pair as possible roots. Compute s as the sum of the pair. Then compute k equals s plus 50. We'll list 4 rows, the 2 positive pairs and their negative counterparts. Step 3. Read off the positive k values. They are 138, 82, and 18. Therefore, there are 3 acceptable positive values of k. In this lesson, we will solve a parameter problem about integer roots of a quadratic. We are given the polynomial p of x equals x squared minus open parenthesis 2k plus 1403 close parenthesis x plus 36. We want all integer values of k for which p of x equals 0 has 2 distinct integer roots, and how many such k there are. We use Vieta's formulas. If our 1 and our 2 are the roots, then their sum s equals 2k plus 1403, and their product p equals 36. Distinct integer roots must multiply to 36. Since the product is 36, list all integer factor pairs with distinct values. We group positives and their negative counterparts. Watch the grid. 136, 218, 312, and 49, and the same pairs with both negative. Here is the key insight. 2k is even, 1403 is odd. So s equals 2k plus 1403 is always odd for integer k. Therefore, we only keep factor pairs whose sums are odd. The pairs with odd sums are 136 with sum 37, 312 with sum 15, 49 with sum 13, and their negatives with sums negative 37, negative 15, and negative 13. These 6 sums are the only possible values of s. Solve 2k plus 1403 equals s for each allowed sum. That gives the 6 integer values of k. Therefore, the integer values of k are negative 720, negative 709, negative 708, negative 683, negative 694, and negative 695. There are 6 such integers. Quick recap. 1. Use Vieta to connect the roots with k. Example: we will solve an exponential equation where both exponents are rational expressions in x, and then report the sum of the real solutions. Step 1. Define a to be the first exponent. Then compute a plus 1 by adding 1 as a common denominator fraction. Combine like terms in the numerator to show that a plus 1 equals the second exponent. Step 2. Substitute into the original equation. We get 3 to the a plus 3 to the a plus 1 equals 324 times root 3. Factor 3 to the a. Divide both sides by 4 to isolate 3 to the a. Write 81 root 3 as 3 to the 4th times 3 to the 1/2. Step 3. Set the definition of a equal to 9/2 and solve for x. Cross multiply, expand, and collect like terms. Step 4. The sum of the real solutions of ax squared plus bx plus c equals 0 is negative b over a. 3x squared minus 19x minus 19 equals 0. The sum is 19 over 3. The sum is 19 over 3. Example: we will find the sum of the real solutions of the given equation. Our key move is to spot the same extra quadratic added to both the numerator and the denominator on the right-hand side. Notice that the right-hand numerator equals the left numerator plus a bridge term, and the right-hand denominator equals the left denominator plus the same bridge term. That bridge is x squared plus x plus 1. So we can rewrite the right-hand fraction as open parenthesis, a plus e close parenthesis over open parenthesis, b plus e close parenthesis. Now cross multiply. Multiply the left denominator with the right numerator, and add the product of the left denominator with the bridge. On the right, multiply the left numerator with the left denominator, and add the left numerator times the bridge. After subtracting the common product, we get the bridge factor on both sides. That gives b times e equals a times e. Now divide both sides by x squared plus x plus 1. This is safe for real x because its discriminant is negative, so it is never 0 for any real x. We obtain b equals a. Bring everything to the right to form a quadratic equal to 0. That leads to 3x squared plus 11x plus 5 equals 0. We are asked for the sum of the real solutions, which for a quadratic x squared plus bx plus c equals 0 is negative b over a. Here, that is negative 11 over 3. In this example, we will evaluate a symmetric expression built from the roots of two quadratics using Vieta's formulas and some clever regrouping. The problem says a and b are roots of x squared plus 2018x plus 1 equals 0. And c and d are roots of x squared minus 2022x plus 1 equals 0. We are asked to find p equals quantity a plus c times a minus d times b plus c times b minus d. First, write the Vieta relations. For the first quadratic, the sum of plus b equals negative 2018, and the product ab equals 1. For the second quadratic, c plus d equals 2022, and the product cd equals 1. Now regroup p as two brackets. Place a plus c with b plus c, and a minus d with b minus d. Expand each bracket in a symmetric way. The first bracket equals c squared plus a plus b times c plus ab. The second bracket equals d squared minus a plus b times d plus ab. Because a plus b is negative 2018, the minus sign gives a plus 2018d in the second bracket. Because c and d are roots of x squared minus 2022x plus 1 equals 0, each of c and d satisfies its own equation. So c squared equals 2022c minus 1, and d squared equals 2022d minus 1. Substitute these into p. Simplify inside each bracket. The c bracket becomes 4c, and the d bracket becomes 4040d. Finally, since cd equals 1, we get p equals 16,160 times 1, which is 16,160. We are told that a is a root of the quadratic x squared minus 4x plus 1 equals 0. We must compute k equals a squared divided by a squared minus 8 a plus 2. Our strategy is to first substitute x equals into the quadratic to get a relationship for a squared, and then use that identity to simplify the expression for k step by step exactly as shown. Step 1. Because a is a root of the equation, substituting x equals a satisfies it. So, a squared minus 4 a plus 1 equals 0. Therefore, a squared equals 4 a minus 1. Step 2. Start with k equals a squared over a squared minus 8 a plus 2. Replace a squared by 4 a minus 1 in both the numerator and the denominator and simplify line by line. To recap, from the root condition we obtained a squared equals 4 a minus 1. Substituting that identity into k causes the denominator to be the negative of the numerator, which makes k equal negative 1. Therefore, the value of k is negative 1. Here is the problem statement. First quadratic x squared minus cx plus d equals 0, with roots alpha and beta. Second quadratic x squared minus ax plus b equals 0, and alpha is a repeated root of this second equation. We must show AC equals 2 times b plus d. Step 1. Use Vieta's formulas on the first quadratic. 4x squared minus cx plus d equals 0, with roots alpha and beta, the sum alpha plus beta equals c, and the product alpha beta equals d. Step 2. If alpha is a double root of the second quadratic, then the polynomial must equal the square of x minus alpha. So x squared minus ax plus b equals the square of x minus alpha. Expanding and comparing coefficients gives it equals 2 alpha and b equals alpha squared. Step 3. Substitute the identities into the target expression. Since it equals 2 alpha and c equals alpha plus beta, their product is AC equals 2 alpha times the quantity alpha plus beta. Distribute to get 2 times alpha squared plus alpha beta, using b equals alpha squared and alpha beta equals d. This becomes 2 times the quantity b plus d, which proves the claim. In this lesson, we will solve a neat coefficient condition problem for a quadratic. We are told that for the quadratic, ax squared plus bx plus c equals 0. One root equals the square of the reciprocal of the other. We will derive a clean relation among a, b, and c. First, recall Vieta's formulas for a monic rescaled version or directly for this quadratic. The sum of the roots x1 plus x2 equals negative b over a, and the product x1 times x2 equals c over a. Now use the given relation. x1 equals parentheses 1 over x2 parentheses squared. Multiply both sides by x2 squared to get x1 times x2 squared equals 1. Replace x1 times x2 by c over a. That gives parentheses c over close parentheses times x2 equals 1. Solve for x2 to obtain x2 equals over c. Because x2 is a root, it must satisfy the quadratic. Substitute x equals over c into a x squared plus bx plus c equals 0. Simplify the fractions. Now clear denominators by multiplying by c squared. This yields the desired relation among the coefficients. In this lesson, we will derive a clean algebraic expression for the square of tangent lambda using only identities and the relationships between the roots of a quadratic. Problem: we have the quadratic x squared plus px plus q equals 0. We name the two roots tangent alpha and tangent beta. From Vieta's relations, we know tangent alpha plus tangent beta equals negative p, and tangent alpha times tangent beta equals q. If cosine lambda equals cosine alpha times cosine beta, compute tangent squared lambda. Step 1. Start from the identity tangent squared lambda equals sine squared lambda divided by cosine squared lambda. Write that also as 1 minus cosine squared lambda all over cosine squared lambda. Step 2. Substitute cosine lambda equals cosine alpha times cosine beta. That gives 1 minus cosine squared alpha cosine squared beta over cosine squared alpha cosine squared beta. Step 3. Split the single fraction into two simpler pieces. It becomes 1 divided by cosine squared alpha cosine squared beta minus 1. Step 4. Use the Pythagorean identity 1 plus tangent squared theta equals 1 over cosine squared theta. Apply it to alpha and to beta. Step 5. Expand the product and simplify by subtracting 1. We get tangent squared beta plus tangent squared alpha plus tangent squared alpha times tangent squared beta. Step 6. To introduce the known sums and products, add and subtract 2 times tangent alpha tangent beta. That groups the first 3 terms as a perfect square. Step 7. Recognize the square. The bracket is tangent alpha plus tangent beta squared. Replace tangent alpha plus tangent beta by negative p and tangent alpha times tangent beta by q. Square negative p to get p squared. Finally, simplify. The answer is p squared plus q squared minus 2q. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.